Foster here. He'll talk today about Schur-Weyl duality for matrix monoids.
Yeah. Hi, everyone. Yeah, so I guess a couple things. I guess I want to just encourage people at any point, if you have any questions, feel free to ask them. I think especially when it's a internal speaker, like we can be a little bit looser with it. So feel free to ask questions. And then this result I'm going to talk about, it's coming out of joint work with Andrew Snowden. It's actually kind of an accidental theorem. So this kind of fell out of a calculation I was doing for some other kind of purposes, and then realized that actually you could think of it this way. Unclear whether it's actually going to appear in the paper we are writing, because it turned out to be not that useful for what we were trying to do. But it's really nice in its own right, so if it doesn't appear there, we'll just write a sort of spin-off paper just about this. But yeah, so let me get into it. All right, so this is a story about Schur-Weyl duality. So let me talk a little bit about what that means, sort of classically, and then get into kind of the variance on it of it. All right, so I'm going to be working over the complex numbers today. So I'm going to have representations happening in characteristic 0 over the complex numbers. It can be any algebraically closed field of characteristic 0, but we'll just work over C. So all right, so I have GLN C. So the general linear group acts naturally on an n-dimensional vector space. And well, the nice thing about group representations is you can tensor them together. So in particular, this means that GLN is going to act on the kth tensor power of this standard representation, and it's going to act by some element G in GLN times a tensor product of vectors V1, V2, tensor Vk. We're just going to act on the the parts separately, independently. So G V1 tensor G V2. All right, so we've sort of taken our defining representation of GLN, tensor with itself a bunch of times, get some new, much larger representation, and we want to understand that. And the way kind of this is done classically is via Schur-Weyl duality. And the observation is that on this space Cn to the k, there's also an action of the symmetric group, Sk, and this Sk is going to permute the tensor factors, right? So if I have some sigma in Sk, and I want to apply it to some tensor product of vectors, I'm just going to permute these vectors amongst themselves. So it's V of 1, tensor 2. Right, so I have these two actions of the general linear group and the symmetric group on the same space. And well, so the theorem, Schur-Weyl duality, classical Schur-Weyl duality, is, well, it's going to kind of come in a couple pieces. So I guess the easy part is these two actions commute with each other. You can kind of just see that. So GLN C and SK, the actions of they commute. But it's stronger than that. So it's not just that they commute, it's that they are each other's centralizers, essentially. So maybe better stated is they, so GLN C generates the endomorphism algebra of this as an SK representation, and then vice versa. SK generates endomorphisms of this as a GLN representation. Right? I should say that in fact, the second statement, so maybe I'll write this, 2 prime is if n is, I think, greater than or equal to k, this bottom one is actually it's an isomorphism, that this that the group algebra of SK is isomorphic to this endomorphism. And that's maybe kind of the more familiar statement for some people, that provided n is large enough, this is this endomorphism algebra is actually just the group algebra of the symmetric group. But even if it's not, it still generates it. You can still permute the factors, and that generates the endomorphism ring. Okay, and then from this setup, we get that this representation that we're looking at, so C to the n tensor k, well, we can decompose it as a GLN cross SK module. And that decomposition is going to look like this. So what's going on here is I have an irreducible GLN representation, it's called vi modules, so W. And I have this is just a tensor product. I write it as a square to indicate that it's an external tensor product. The two groups are acting on the separate sides kind of independently, as opposed to this kind of tensor product where it's one group acting diagonally. But it's just a tensor product of vector spaces. And this is then the Schmeck module for the symmetric group. Right? And well, I should say, so lambda here, in this case, is going to run over so partitions of size k with less than or equal to n parts. Right, so kind of we typically index both representations of general linear groups and symmetric groups by partitions. For symmetric groups, it's partitions of k, this k, and for GLN, we get partitions of at most n parts. Okay, so that's kind of both of those conditions there in this statement. And so what I want to kind of say is that this one, so this is really nice. This is really kind of, in some sense, a corollary of this double centralizer property. So anytime you have a double centralizer property, you get a decomposition like this, where you have one irreducible on one side matched with another irreducible on the other side, and there's no repeats, right? So a double centralizer property kind of gives you a way of matching up some irreducible representations between these two groups or algebras or whatever we're having a double centralizer property for. And in some sense, it justifies the fact that we're using the same labeling system for these, right? So this is actually, depending on the source, this is often somehow sometimes how people define the Schreck modules for the symmetric group is via this labeling. All right, so this is kind of classical Schur-Weyl duality. So it gives us a lot. It gives us like this really powerful dictionary between representations of general linear groups and representations of symmetric groups, and you can kind of transform statements between them using this, right? And so often something that you're interested in might be easier on one side than the other. Yeah.
Sorry, so how do you get from just writing your W lambda in terms of that partition to just getting like a weight or some sum of weight?
Yeah, so the lambda is a sort of highest weight, right? So if lambda is, let's say 2, 1, right? That means that I'm looking at the representation of GLN where the highest weight is, how I would like to think of it is, I have my torus inside GLN, and the weights are going to be weights of this torus, which are representation of this torus, and highest weight 2, 1 means I have x1 squared x2 as an eigenvalue, and that's kind of the the lexicographically first eigenvalue that occurs. So that's the sort of dictionary between the highest weight theory. Yeah, it's a little, if you try to write it in terms of like fundamental weights, it looks a little bit different, but that's kind of the easier way to think of it as partitions. Any other questions? All right, so this is classical Schur-Weyl duality. And now let me talk about, we often refer to Schur-Weyl duality not just as this, but as kind of similar types of statements. So there are a bunch of kind of variations of this that occur. Let me mention a few of them. So in all these examples, I'm still going to have my underlying space be C to the n times k. And sort of classical Schur-Weyl duality, I had GLN and SK acting on this. And we can kind of, if we change one side, we have to change the other side accordingly. So for example, if I want to think of Cn instead of as a GLN representation, I could say think of it as a representation of the orthogonal group. Right? So now I've shrunk this group, which means I'm going to have more things over here that commute with it. Right? It's easier to commute with a smaller group. So it turns out what goes over here is something called the Brouwer algebra. And what you can kind of think is, if the symmetric group I think of as permutations, so I can write this as the permutation that kind of swaps 2 and 3. The Brouwer algebra is a little funny. It's spanned by things where we also can I can have some caps and cups between things. So it kind of connects up in different ways. But let's not get too much into that. So another thing I could do, switching up this GLN, I could take GLN, and instead I could take the the quantum group associated to it, or maybe here I'm writing the quantized enveloping algebra. And then over here, we get the Iwahori-Hecke algebra acting on acting on the right-hand side. And this gives us, again, a nice way. So if Q is not a root of unity, both sides have semi-simple representation theory. You get the nice decomposition. That's actually kind of everything is the same dimensions as the ordinary Schur-Weyl duality. What are some other examples? So sitting inside GLN, I could take the symmetric group. Right, so Sn sits inside GLN as permutation matrices. Right, and so then I could say, well, what commutes with it over here? This is now called the partition algebra. So this is, again, kind of a bigger algebra than the symmetric group algebra. You can think, in terms of these diagrams, you now also have things that kind of merge some stuff on the top, or maybe I send like all three of these up top to these two on the bottom. There are some additional diagrams, and there's some parameters that show up in these ones. But they're nice kind of algebras that are very diagrammatic. All right, and I could go on. So there's a bunch more. So I could take GLN. I could say, well, instead of the full GLN, what do I take? GLN minus 1. Well, then I would replace the symmetric group by something called the Rook monoid. So this is like the symmetric group, but now I'm allowed to have some of my dots on top and bottom not connect to anything, but otherwise it's sort of injective. But all right, I can go on. There's a whole bunch of these. So in all of these statements, we get some version of this whole theorem, right? So I have these two commuting actions. Either in this case it's two groups, but often it's like a group and an algebra, or maybe two algebras. We have these two commuting actions. They generate each other's centralizers, and at least in the semi-simple case, so all of these, except maybe this one when Q is a root of unity, that gives us this nice decomposition where we can match up irreducibles on one side with irreducibles on the other. And it gives us a matching between the irreducibles of these two groups or algebras that occur inside this representation.
Oh, in the root of unity case, we don't know 3
Yeah, in the root of unity case, I mean,
as a bimodule.
I think we don't
know
expect it to look like that on the nose, right?
No, it's not.
Right, because you'd have extensions.
Yeah, they're tilting modules.
That's right. Yeah, so the non-semi-simple case is super interesting. So often we still get 1 and 2, and well, sometimes 2 prime, whether we care about that. But that doesn't quite give you as much. So this also happens when we look at modular representations. So I could look at same thing, GLN and SK, but in characteristic P. And yeah, the story there is very similar. We have a nice double centralizer property, maybe assuming n is sufficiently big for decay, but that doesn't give us this decomposition on the nose. Instead, it gives us a pair of functors between the representation theory of general linear groups and the representation theory of symmetric groups. And those aren't equivalences of categories, but they're adjoint functors that can give us a lot. And that's actually one of like the best tools we have for studying the representation theory of symmetric groups in characteristic P. I guess, or representations of general linear groups, but somehow algebraic groups are like a little easy. There's like more tools. So often the dictionary goes from GLN to SK, but it can go both ways. But yeah, so this is Schur-Weyl duality, and it's many variants. But okay, I want to briefly mention a favorite open problem of mine. So when we have a double commutator theorem, we get this really nice kind of pairing of the irreducibles, this really nice decomposition of it as a bimodule. But if we don't have that, if they just commute with each other but aren't each other's entire centralizer, it becomes a lot harder. So the problem is decompose C to the n tensor K as a Sn cross Sk module. Right, so I have permutation matrices sitting inside GLN. That commutes with permuting the tensor factors, right? But the decomposition, they're not going to match up perfectly anymore. It's going to be some mix of things. So this problem is equivalent to understanding how to restrict an irreducible representation of GLN to the copy of the symmetric group Sn sitting inside it. And so we have some multiplicities arising, and we don't understand those. So this is called the restriction problem in combinatorial representation theory, and it's hard. We don't know the answer. But I'll say, like, as a just problem about kind of symmetric groups, it's very like enticing, right? So this space, this is just isomorphic to, I'm just going to look at functions from, say, a k element set to an n element set, and then I'll linearize it. And my two actions are, right, I can act by precomposition by Sk or postcomposition by Sn, and those two actions commute. And I'm just asking to decompose this as a Sn cross Sk representation, but we don't know how to do it. All right. So now, what I want to talk about today is I want to take this problem and I want to make it seemingly harder. So what I'm going to do is I want to, so today, what I want to do is kind of look at a version of this problem and Schur-Weyl duality where I'm going to replace Sn by the group GLN-FQ. Okay, so invertible n by n matrices over a finite field FQ. I'm still going to be working in characteristic 0. So right, this is a finite group, so I can take representations of it just over the complex numbers, like any other finite group, and that's what I'm talking about. So we could also look at representations over FQ, or maybe over an algebraic closure of FQ, and it's a very different story. Very interesting story, but it's not the story I'm going to talk about today. Okay, so let me say a little bit about the representation theory of GLN-FQ, because it's probably less familiar to people than the symmetric group. It's definitely more complicated, but it's not so bad. So the representation theory of GLN-FQ is sort of built up largely kind of inductively. So if I have GL and FQ, well, okay, sitting inside of it, I can take like GLA, FQ, maybe GL n minus A, FQ. I could keep going. I mean, I could have more than 2 parts, but I'll just do it for 2 for now. Right, so this is a Levy subgroup sitting inside there, and then if I allow myself to have stuff in that upper right-hand corner, but then nothing down here, this is going to be a standard parabolic subgroup. And so one thing I can do to kind of inductively build my representations of GLN is I can take a representation of GLA. So I could take V, GLA, rep, and then I could take a representation of GL n minus A, call it W. And so what I could do is just take these representations, right, tensor them together, so now this is a representation of GLA cross GLN minus A. And I could just induce it up to GLN. And that, like, is a thing that you can do. It gets pretty messy pretty fast. But we have a better way of doing it. So we take this representation of GLA cross GLN minus A, and we can actually inflate it to this whole group, this whole parabolic group, by just letting the stuff up here act trivially. Right? So if you like, we have a homomorphism from this group to just the product of these 2 groups, where you just ignore what's up there. Right? And then this representation of the parabolic subgroup is just pulling back along that homomorphism. So I take this, and then so I'm going to call this, I inflate. So I'm going to inflate it from the Levy to the parabolic, right? So that just means act by the Levy part and ignore the kind of generally unipotent part. And then I'm going to induce from this parabolic up to GLN, right? And this is called parabolic inversion. So this composition it's a composition of 2 functors. It's a very nice operation. It's much nicer than just naively inducing your representations. And so the way that you get at representations of GLNFQ is sort of inductively, right? You look at representations that occur inside a parabolic induction, and then you look at the stuff that does not appear inside a parabolic induction. So all right, so we have parabolic induction, and then we say that so chi a irreducible representation of GLN is custodial if chi does not appear in any parabolic induction. Right, so these are kind of the new representations that are like new to GLN, not coming from some smaller GLA or GLB. And so these are a little bit harder to describe, but they are in correspondence with something that's pretty easy. So I can look at GL1 of FQ to the n, sitting inside right? So I can think of fq to the n as a n-dimensional vector space over fq. So I can identify this with fq to the n. And then multiplication is acting by invertible linear transformations. So I have a natural embedding of just the multiplicative group of this field extension inside this. And these custom representations are in one-to-one correspondence with characters of this. Right? This is an abelian group. Characters. So this is kind of where they come from. You can imagine, take a character for this group and then induce it up to the full GLN of Q. That is not how you construct the custom representations, but kind of morally something similar happens. So there's something called Deligne-Lustig induction, which is kind of doing that a little bit better than the naive induction. But they differ by something that we kind of understand. Turns out they differ by like Steinberg tensoring with some specific thing. With Steinberg. But okay, so this is kind of where they're coming from, these custal representations. And well, the idea is the representations of GLN FQ are these cuspidal things, along with, well, you take a Levy factor, so maybe not just two things, but more than two. You take a cuspidal thing for each one of those, and then you parabolically induce it up. And all representations occur in those. If you pick a different cuspidal representation for each factor, that parabolic induction is actually irreducible. So you're done. If you have any repeats, then there's some partition combinatorics that happens. So kind of the data involved in indexing all representations of GLN is understanding these cuspidal representations of all GLMs up to n, along with partition data. Right, so it's a kind of hybrid of some kind of more familiar symmetric group combinatorics with partitions and kind of characters of these different types of tori inside GLN of Q. So that's kind of a very quick overview of that. I know that was a little fast, but I want to give you kind of the flavor of it. What's going to be really kind of important for the story going forward is this parabolic induction functors are going to show up. And what maybe the takeaway is, we understand this really well and what it does to irreducibles. So like I said, often, if I just take two different cuspidal representations here, the parabolic induction is itself irreducible still. And if it's not, if we kind of repeat some cuspidal factors, we understand how that decomposes. So it's more complicated than just the symmetric group story, but not so bad. All right. So let's bring this back to the world of Schur-Weyl duality. So any questions? I know that was fast.
So how does the Heck algebra come into this?
Yeah, so the Heck algebra will show up in the following way. So GLN FQ, this is going to act on the flag variety over FQ. So this full flags over FQ. And then it'll act on, let's say, the linearization of that. The endomorphism algebra of this is the Heck algebra
Yeah.
at Q.
Yeah, I was just thinking of induction from the Borel up to that and taking the,
Yeah, so under this description I was talking about with these cuspidals, the ones that appear here are where you're taking Levy factor that is just one, so it's like GL1 cross GL1 cross GL1 cross GL1,
right.
and you're taking the trivial representation on all of them. So those are kind of very special class of representations. They're called unibundle representations, and they're exactly the ones that appear in this. Yeah, I mean, this is a beautiful story, but it's not quite the story I'm telling today. So instead of flags, I want to go even simpler than flags. So GLNFQ acts on FQ to the n, right? By just ordinary multiplication. Okay. So then it also acts on CFQ to the n, right? FQ to the n is a finite set. So I can take, say, formal linear combinations of it. Or if you want, you can think of this as like complex valued functions on FQ to the n. And this often plays the role of sort of a defining representation for the characteristic zero representation theory of GLNFQ. All right, so that's kind of that's going to be our defining representation. So I mean, this is a big space, right? So this is like C to the Q to the. This is a big representation. But I will say that the smallest non-trivial representation of GLNFQ in characteristic zero is about this divided by Q minus 1. So it's about C to the Q to the n minus 1. So this is actually not that much bigger than the smallest possible thing you could take in characteristic zero. This is not irreducible. It has, we'll maybe talk about its decomposition in a bit. But okay, so this is going to be my kind of defining representation that I want to get a Schur-Weyl duality statement for. So okay, we can do kind of the crazy thing, and I'm going to look at CFQ to the n tensor k, right? So to be a Schur-Weyl duality statement, I should take some sort of defining representation and look at its kth tensor powers. Okay, so now what's going to act on this? Seems hard, but it's not so bad. So one thing that's true is that's nice about when you are linearizing the action of a finite group on a finite set, is that tensor products correspond to just products of those sets. Right? So really this is isomorphic to, okay, so it's the linearization of FQ to the n times FQ to the n times FQ to the n times. Right? This is just anytime you take a tensor product of two permutation representations, so linearizations of actions on finite sets, that corresponds to just the linearization of the product of those sets. Okay, but this now is the same as FQ to the n tensor FQ to the k. And GLK FQ acts on this by acting on this factor. And actions commute. So I have this tensor power of GLNFQ naturally carries a GLKFQ action on it. All right. So this point, so this is not new. So this you can say okay, well, I want to decompose this as a GLN cross GLK representation. Problem is these are not in Schur-Weyl duality with one another.
Mhm.
They do not generate each other's centralizer. So we don't expect it to be a nice decomposition where it's just one irreducible tensor, an irreducible on one side, tensor irreducible on another side. And in fact, that's just not true. So all right, but it's still some things that people have said. So it turns out you can kind of make it sort of work. There's something called the theta correspondence that appears in the automorphic forms literature that kind of allows you to pick up a particular factor. If I look at the isotypic component for a GLN representation, it'll have multiple GLK factors, but you can pick up one. There's a way to kind of pick one out, and that's what they call the theta correspondence in that world. But I want to do better than that. I want to upgrade this to a Schur-Weyl duality statement. And the claim is that, so I have, GLN is acting on FQ to the n, just normal matrix multiplication. Same thing with GLK. But actually something a little bit bigger acts on this. So here I'm taking invertible n by n matrices acting on an n-dimensional vector. But I actually could take all n by n matrices. And this action still makes sense. Right, so I actually can enlarge this to the monoid of all n by n matrices, not just the invertible ones. And similarly, I can enlarge this to the monoid of all k by k matrices over FQ, not just the invertible ones. All right, so these are bigger, they include more stuff. But all right, now let me state the theorem. Well, the theorem is these are in Schur-Weyl duality. So M and FQ and M KFQ generate each other's centralizers. In this space, this C, F, Q to the N. That's okay. So they generate each other's centralizers. Yeah, so that's the theorem. Okay, so they're in Schur-Weyl duality. Right? But okay, you might be like, well, why is this at all useful? So this is the thing that we accidentally proved. But here's why it's nice. Here's why this actually tells us something. This has semi-simple representation theory. I mean, so does MK. Moreover, it's not just that it has semi-simple representation theory, it's actually like pretty easy to understand if you understand the representations of the general linear groups. So let me say what they are. So irreducibles these are in bijection with GL, M, FQ. Maybe I should write the union over M, where. Right, so I take all the irreps of the general linear groups up to N, and those index the irreducibles for this matrix monoid. Moreover, the bijection is actually really simple. What you do is you take GL M here, GL and minus M. I take this Lemme factor, and I just do parabolic induction. Where I take whatever my irreducible of GLM I want, tensored with the trivial representation of GLN minus M. So this sort of describes what it is as a GLN module. But importantly, this thing is going to have matrices with rank less than M act by 0. And then matrices with rank bigger than M don't act by 0. So right, these representations, they're sort of distinguished by how matrices of lower rank act from one another. So this is our the description. So in particular, we completely understand how the irreps look as representations of GLN FQ. We understand parabolic induction pretty well. It has kind of partition combinatorics. So
So I have a question. So suppose you take the endomorphism algebra of MKFQ on the tensor space. Okay, so yeah.
MK and FQ on this.
Right.
Great.
So you get some algebra. And is that algebra related to MNFQ at all?
Yeah, if if n is bigger than k. No, sorry, if k is bigger than n, it is MNFQ. You get all the irreps occur, and so you actually just get MNFQ.
So you don't get degree D polynomials in that or anything like that? That's kind of how the other case works. You know, you sort of split like polynomial representations of degree k, for example.
No, so these kind of mix up. So when you're looking at this tensor k, you're going to see things. It's not graded the way that like ordinary GL n representations are. Yeah. You see things appearing in multiple degrees.
I see. Okay.
Yeah. So that's the. All right. Let me kind of real quick say what this kind of gives us. So I can take my CFQ to the n tensor k. I have this nice decomposition. I have to underline. Let's call it lambda tensor I should use n. Sorry, call it W. N was algebras themselves. So I have I have a decomposition, and well, one thing that's true is that it's this labeling by the irreducible representations up to some size is compatible with this duality statement. And so I get the representations indexed by the same thing, right? So this lambda should be running over the irreducible representations of smaller GLMs, smaller than both n and k, so whichever one is smaller kind of determines what shows up and what doesn't. So this is as a bimodule for these two monoids, right? But then we actually know how to restrict these to GLN and GLK. So we actually can further restrict this down to GLN cross GLK. And it's a little bit messy to write because you need to write down what the sort of branching coefficients are. But they are just essentially literal Richardson coefficients. Right, so we can kind of get a decomposition of this space as a GLN cross GLK bimodule. And the coefficients that are occurring are essentially products of certain literal Richardson coefficients, which determine the restriction from this matrix monoid to the general linear group. So this basically completely answers this question that I really love about the symmetric groups, where I want to decompose it as a Sn cross Sk module. But it does it for GLN cross GLK, and I still don't know how to do it for the symmetric groups. So yeah, that's the story there. Yeah, any questions?
I have a question.
Yeah.
I have a very dumb, naive question.
Great, I love those tags.
Whenever I enlarge GLN to all matrices, I want to think of it as a ring rather than a group.
So in this case, we want to think of it as a monoid.
Right.
So it's,
that's
yeah,
what I said.
we're still not adding them, but we're just multiplying them, but now we've thrown in matrices of lower rank. And in monoid land, you have things that are kind of like ideals. So right, so if I look at matrices of rank at most J, that forms a kind of ideal in the monoid of matrices, right? Because once you have a matrix of rank, J or less, there's nothing you can multiply it by to make its rank bigger. So GLN is actually kind of sitting inside this monoid as a quotient, where we quotient out by the ideal of lower rank matrices. And that's actually how this thing kind of works in the case where if I take M to be N, then the representations of GLN, I can think of them as a representation of the matrix monoid by just making everything of lower rank act by 0. But there are extra representations of the matrix monoid where they don't act by 0. So maybe as an example, if I look at GL1 sitting inside 1x1 matrices, so as simple as possible, this monoid actually has sort of two trivial representations. So one of them is going to be the representation where every matrix acts by the identity. And the other one is going to be one where the invertible matrices, so just the non-zero elements, act by the identity, but 0 acts by 0. And so this matrix monoid, we've kind of broken up the trivial representation of GLN, and we can enlarge it in two different ways. And that's exactly what sort of happens over here, is that these representations that we're getting using parabolic induction, these are actually often irreducible themselves, but we're extending them to the monoid in different ways by sort of saying, what do matrices of lower rank do? And yeah, the ones corresponding to GLM are exactly the ones we get by making matrices of rank less than M act by 0. So there's this sort of hierarchy of the monoid representations.
You may want to mention, when you take an algebraically closed field, so replace the finite field by an algebraically closed field, then the monoid representations correspond to the polynomial representations of
So yes. So if I take GLN C sitting inside MN C.
Right.
So you can ask which representations of GLN extend to the matrix monoid, and they're exactly those that are the polynomial representations.
Right.
So you don't have to, you never invert the determinant.
Yes.
Right. However, there is a subtlety here. There are more representations of this that are not continuous.
Mm-hmm.
So, so for example, if I just look at the action on C to the n, there's another representation of this one where I just say any matrix of rank less than n acts by 0.
Mm-hmm.
And that is just the same thing on the GLN for the GLN action, but it's a different monoid representation.
Mm-hmm.
Turns out if you impose that this acts continuously, then they actually agree.
Right.
But there is a slight difference there that's sort of analogous to this story.
Right.
But yeah, so I guess I was saying it's kind of fun mystery to me why this doesn't work for Sn cross Sk. So I'm having GLN cross GLA I can think of this as acting on the space of, let's say, n by k matrices, where I'm acting on the right and left. Maybe I have to twist one of them to make it a left action as I find it. But this is very analogous to the space of functions from k to n, right? This is like the space of linear functions from fq to the k to fq to the n. And so somehow the fact that this doesn't work for symmetric groups is mysterious to me. But yeah.
I guess I have another naive question. Do you have an extension of the action of GL and FQ on some delineation variety to this bigger monoid?
I don't know that anyone has thought about that. Somehow monoid representations are not in fashion. I don't know. They're not something that people think about a lot. But they are occasionally very, very useful. And in this case, they sort of exactly package how you want to type. Yeah, I don't know. That's an interesting question. In my mind, Deligne-Lustig theory is really good at making these sort of customary representations. And parabolic induction is great on its own. And you don't, if you're trying to construct a representation that, I would say it would be easier to do Deligne-Lustig theory on the Levy pieces and then parabolically induce up, rather than just try to do Deligne-Lustig theory on the whole thing. You can, but I think maybe you don't want to. And so I kind of think that maybe in this case it wouldn't be a super different story, because all of the customary representations sort of are only occurring at this kind of top rank case. And then we would just maybe extend it by 0, the non-full rank matrices. So maybe my guess is there's not a lot of interesting story there, but I don't know.
Other questions? If not, let's